thank you very much for the invitation and for the presentation. And thank you to Anna to start the lectures. I will a little bit continue with the topic that Anna started, and I will talk about the Chern-Weil theory and Hilbert-Samuel theorems for semi-positive singular toroidal metrics, and then applications to Siegel-Jacobi modular forms. And what I will explain is joint work with Anna Botero, David Holmes, and Robin de Jong. So I will start recalling a little bit again what are B divisors, but then also introduce the other two main actors of this history, which are graded linear series and PSH metrics with toroidal singularities. So let me start recalling what Anna has already explained to us about what are toroidal B divisors. So I fix X a smooth complex variety, maybe a compact one, and then B inside X will be a simple normal crossing divisor. Then by delta of XB, I think in Anna's talk was R of XB, this delta will be the conical polyhedral complex associated to these simple normal crossing divisors, the delta XB. Then by divisors of XB, this will be the space of Cartier R divisors on X whose support is contained in the fixed divisor B. And then R of XB will be the set of all allowable modifications of this pair XB, which are in bijective correspondence with rational subdivisions of this polyhedral complex delta of XB. And then the B Cartier divisors, the toroidal Cartier divisors, will be just the direct limit of all proper modifications that are toroidal of divisors supported on B and the exceptional divisor. And there is a one-to-one correspondence, as Anna explained already, between the space of B Cartier divisors and the space of all piecewise linear functions on this polyhedral complex that has a rational fan of linearity. So the fan of linearity has to be defined over the rational numbers, while the Weil B divisors, the toroidal Weil divisors, will be the inverse limit with respect to all toroidal modifications of this space, and these are in one-to-one correspondence with the conical functions on the set of Q rays of this polyhedral complex, but without any continuity assumption. It's just the set of all conical functions, so a very wild object. And then, in particular, a Cartier B divisor will be just a divisor in a single model, while a Weil B divisor will be a collection, as Anne explained to us, of divisors, one on each proper modification, with a compatibility condition that if I have a map of modifications, then the push forward of the divisor in D prime has to be the same as the divisor. So it's a collection of divisors that are compatible under push forward. And as Anne explained to us, there is also the non-toroidal version, where one considers all possible smooth projective modifications instead of only the toroidal ones. Then it's good to restrict to the net ones, because the net one has much more positivity conditions. So B Cartier divisors and Weil divisors have a topology. And as Anne also explained, since for every modification, we have the property that if we take the pullback of a divisor and then the push forward of the divisor with the identity, then we get injective maps between the divisors on XP with support on BP, then the B Cartier divisors on XB, and everything is included in the Weil B divisors. We have canonical injections like this. Then we will take as deep X pi B pi plus will be the space of net divisors, and B Weil divisors plus will be just the closure with respect to the weak topology of the union of all Cartier net divisors. And then there is this theorem of Dang and Fabre in the general case, and also Botero and myself in the toroidal case, that if we have a NEF Weil B divisors, then we can always find a sequence of Cartier B divisors, NEF, that converges to the divisor, and monotonically. And in this sequence, if we consider the degree of each of the elements of the sequence, so the alpha to the d, then the limit when alpha goes to infinity exists. It is a real number. It's independent on the sequence that we use to approximate the divisor, and is what we define as the degree of the B divisor. Then this was the first actor, a quick review of B divisors. Now the next actor will be graded linear series. Then again, I have my complex variety X, and then I consider F to be the field of rational functions on my variety X. And then a graded linear series is just a subalgebra of the ring of polynomials with coefficients in F. So it's a subset of a subalgebra of F of T. And if L is a finite dimensional subspace of the ring of function fields, then we will define A sub L will be the subalgebra generated by L in degree 1. And we will say that a graded linear series A is of integral type if there exists a finite dimensional subspace L such that AL is contained in A, and A is finite over AL. So it's very close to an algebra of the type AL, but not necessarily the same thing. So this will be of integral type. And graded linear series is called of almost integral type if it is included in an algebra B and B is of integral type. So these are the interesting for us graded linear series. So the subalgebras of F of T that are contained in an algebra of integral type. And we will use the following notation. So since it is a subalgebra of F of T, we can divide in degrees, and then we will write A will be the direct sum of AL T to the L, where AL is a sub-vector space of F. And for instance, if I have a divisor on X, then L of D is just the set of all rational functions different from 0, such that the divisor of F plus D is effective, union 0. And then the graded linear series associated to the divisor D is just taking the direct sum for all L bigger or equal than 0 of L of this multiple L times D multiplied by T to the L. And one can see that for all divisors D, R of D is always of almost integral type. And this is easily seen because if D is ample, then it is of integral type, and then any divisor has an ample divisor that is bigger than this one. And this gives automatically the fact that for every divisor, the algebra, the graded linear series R of D is of almost integral type. Now, the third actor will be toroidal singular Hermitian metrics. So again, I have my complex variety. I have B simple normal crossing divisors. Then U now will be the complement of B. And I have L a line bundle on U. And now I have or let's say no, L is a line bundle on the whole X. And a singular metric will be called PSH toroidal metric with respect to B if it satisfies the following properties. The first one is that it has to be continuous on U, so it is a continuous metric outside B. In fact, we can use weaker conditions. So in some sense, we only need that this metric is locally bounded. But for simplicity, let's assume that the metric is continuous on the open set U. The second condition is that for every point on X, if S is a rational section of L, but that is generating in a neighborhood of B, so I have S as a generating section of L on some open set B around X, then I consider the function F, which is minus log of the norm of the metric. Then I want that this function on B is plurisubharmonic. That means that it is a function from B to R union minus infinity, which is upper semicontinuous, that is locally integrable, and that DDC of F is a positive current. And then the third condition is that if now B is a coordinate neighborhood in which the divisor B is given by the equation Z1 up to Zk equal to 0, then this function f, the logarithm of the norm of the section, can be written as a function g that only depends on the logarithm of the variables Z1 up to Zk, plus a second function eta, that now this function depends on all variables. But eta is a function which is locally bounded, so does not introduce any serious singularity. And the function g has to be a convex function. So it's a convex function evaluated in minus log of Z1 up to minus log of Zz, and then this locally bounded function. So this is a PSH toroidal metric. Now, let's see how these three objects, on one hand, singular toroidal PSH metric, on the other hand, graded linear series and B-divisors, play with each other. So for instance, how we can go from toroidal PSH metrics to B-divisors. So I have X, B, U, and L as before, and I have this S a rational section, and let's say it's generating on some point X, and I have my PSH toroidal metric. Then we will define the B-divisor associated to S, L, and the metric is a B-divisor which is defined using what is called the Lelong numbers of the singular function f. Now, it turns out that this B-divisor is always an f B-divisor, and if I look at this B-divisor D and I subtract the divisor of S, which is an ordinary divisor, then this is always a toroidal B-divisor. If my PSH metric was a toroidal singular PSH metric. Then D minus ds corresponds to a conic function, phi of D, on this polyhedral complex. And let me characterize this function phi of D, because in some sense this will tell us who this B-divisor is. So then let's fix B a coordinate neighborhood such that the divisor intersected with B is given by Z1 times Zk equals to 0. Then the stratum S, where Z1 up to Zk are all equal to 0, this is a stratum of the normal crossing divisor, and it corresponds to a cone in this polyhedral complex. This will be sigma S, is a cone in delta of xb. Now, we also know that my minus log of the norm of S will be given by a convex function g plus this locally bounded function eta, as before, and then the function phi d on the cone sigma S is given exactly by minus the recession function of g, which means that I have to take the limit when lambda goes to plus infinity of 1 over lambda g of lambda x. So you see the function g was a convex function on minus log of Z1 up to minus log of Zk. And then the recession function is just looking at the asymptotic behavior of this function. So it's a conical function that gives us exactly what is the asymptotic growth of the function g. This determines a function on the cone sigma S, and this function gives me a B-divisor on this toroidal B-divisor on this variety. Okay, so this is how one can go from toroidal PSH metrics to B-divisors. In some sense, the B-divisor comes from the asymptotic of the singularity. Now, how we can go from graded linear series to B-divisors and back? If I have a graded linear series of almost integral type, then I can define the B-divisor of A, and this is given by an tuple of divisors, one on each toroidal modification. And the B-divisor on a modification pi will be just taking the infimum of all divisors on x pi, such that L of E plus the divisor of F is bigger or equal than 0 for all integrals L and for all functions F in AL. In general, this will be a B-divisor that is not necessarily toroidal unless the linear series is of some special type. And in the other direction, if I have D a B-divisor, then I can define exactly as we define it in the case of ordinary divisors, I can take L of D will be the functions, the rational functions different from 0, such that d pi plus the divisor of f is effective. So all coefficients are positive. For all proper modifications, union 0. And then we define R of D just the direct sum for all integrals L of the linear series associated to the divisor LD times T to the L. And this will be a subalgebra of FT of D. Okay, so now we have gone from metrics to B divisors and B divisors to graded linear series and back. And now how to go from toroidal PSH metrics to graded linear series. So now I have, as before, my complex variety, my normal crossing divisors, the complement U, my line bundle L, and I have this metric, which is PSH and toroidal, and I fix a section S. Then we will define L of the line bundle, the section, and the metric will be just the set of rational functions such that the norm of f multiplied by s is bounded. So I am looking at, in some sense, sections, rational sections of my line bundle such that the norm is bounded. And then we will define R of L, S, and the metric will be just the direct sum for this graded this linear series associated to the different powers of the divisor L. Okay, now what are the different compatibilities of these notions? So there are easy compatibilities. For instance, if I have a divisor that is smaller than a second divisor D prime, this means that D prime minus D is effective, so all coefficients are positive. Then one can see that the graded linear series associated to D is contained in the graded linear series associated to D prime. And in the other direction, if I have a graded linear series A that is contained in a second graded linear series A prime, then the B divisor associated to A is always smaller or equal than the B divisor associated to A prime. Then if I start with a B divisor, then I look at the graded linear series associated to this B divisor, and now I take the B divisor associated to the graded linear series. It is not true that I recover the original B divisor. What is true is that I recover a B divisor which is smaller than the original one. And on the other direction, if I start with a graded linear series, I look at the associated B divisor, and then I go back to linear series, then what I obtain is a graded linear series that in principle will be bigger than the original one, but not necessarily exactly the same as I had before. On the other hand, if I start with a line bundle, with a section and a metric, I can go directly to the associated graded linear series, or I can start going to the B divisor and then to the graded linear series. Then these two things are not equal, but what I can say in complete generality is that if I go directly to graded linear series, this will give me a smaller graded linear series than if I first go to the B divisor and then I go to the graded linear series. So these compatibilities are easy to see. But in the toroidal case, we can do things slightly better. And in the toroidal case, if B is the boundary divisor, then if I look at the B divisor associated with the line bundle L, the section S, and the metric, and I subtract a small quantity of the boundary divisor B, then I obtain a graded linear series which is smaller than the graded linear series that I obtain directly from the divisor. And you see that then I get some kind of a sandwich because I have the graded linear series associated directly to the line bundle, which is contained in the graded linear series associated to the B divisor, but contains the graded linear series associated to the B divisor as long as I have made a small modification. I have subtracted a small multiple of B. Okay. Now, what are other properties? If I have a Weil B divisor, then I can define the volume of this Weil B divisor. This volume will be given by the lim sub. I look at the dimension of the associated graded linear series, the different graded pieces, and then I take the dimension of RDL divided by L to the D factorial. I look at this lim sub, and this will be the volume of my B divisor. So this is in complete analogy of the definition of the volume of a divisor. And we'll say that my Weil B divisor is big if and only if this volume is strictly bigger than 0.
Is this
And
secretly
then we have
a,
this.
oh, excuse me. Is there secretly a volume of some Newton-Coulomb body?
Yes. In some sense, the point is that this is very much related. So whenever you have a linear series of almost integral type, you can associate a Newton-Coulomb body, and this will be related to this volume of the Newton-Coulomb body. Yes.
I see. Okay, thanks.
Mm-hmm. And then we have the theorem with Anna, David Holmes, and Robin de Jong that if D is a big and nef toroidal B divisor, then the so recall that I was saying that in general, if I start with a divisor D, I look at the graded linear series and I go back to B divisors, I obtain something which is smaller than D. But in the case of a big and nef toroidal B divisor, it turns out that if I start with the B divisor, I go to the graded linear series and then I take the B divisor back, then I recover the original B divisor. So nef and big toroidal B divisors have better properties than general B divisors. And as a corollary, if I have a line bundle with a toroidal PSH metric, and I assume that the B divisor is effective, and that the boundary divisor is contained in the support of this B divisor. This is a small technical condition that can always be achieved if I modify a little bit the section S, if the line bundle is sample, for instance. Then the B divisor of the graded linear series associated to L, S, and H again is equal to the going directly to the B divisor. So in the world of toroidal and nef objects, we have better properties than in the general situation. And also we have a result that will be important later. If I have a graded linear series, in general, this graded linear series will not be finitely generated. But we can give a criterium for finite generateness, at least a necessary criterium, that tells me that if I have a graded linear series that is finitely generated, then the associated B divisor is always a Cartier B divisor. And this implies in particular that the function phi of D, the associated function, is a piecewise linear function. So this result will be important later. Okay, and then I recall what Anna already said, that we have a Chern-Weil theorem, at least for line bundles with toroidal PSH metrics, that relates the self-intersection of the associated divisor with the integral on the open part of the first Chern class to the D with the volume of the associated graded linear series. And I want to note that recently Chia has sent to the archive a very nice paper where he extends this Chern-Weil result not just to line bundles but to vector bundles using Segre classes. So this is a very nice recent preprint. Okay, so this was the setup. So we have these B divisors, the line bundles with PSH metrics, and we have the graded linear series, and they are linked together, and we have very nice properties in the case of toroidal and other things. We have a lot of compatibilities. And now we want to apply this result to Siegel-Jacobi forms. So Siegel-Jacobi forms are the analog of modular forms, but on the universal abelian variety. So let me give the more or less the formal definitions of Jacobi forms. So first I need to introduce the Jacobi group. And to introduce the Jacobi group, I start with a symplectic group. So the symplectic group of dimension or of degree 2 times G is a set of all 2G by 2G matrices that can be broken into 4 components, A, B, C, D, and that satisfies the condition that A transpose times C is equal to C transpose times A. This is just the same as saying that A transpose times C is symmetric. D transpose times B is also symmetric, but we also have the condition that A transpose times D minus C transpose times B is equal to the identity. This condition, in some sense, is just the same as saying that these are the matrices that respect the symplectic linear form. And this is a subgroup of GL to G set. Now we can embed the symplectic group of degree 2G inside the symplectic group of degree 2G plus 2. Just as follows. So I take the matrix A, B, C, D, and then I construct a matrix where the A I enlarge a little bit with one dimension, adding one in the diagonal. I enlarge B, just adding zeros. I enlarge C, just adding zeros. I enlarge D by adding one at the diagonal. And it turns out that now this matrix is symplectic of degree G plus 1. Now we also consider the Heisenberg group. The Heisenberg group H of C is just like a lattice, a 2G lattice with an extra element. So Hg of C is the set of elements lambda mu x, where lambda is in set to the G, mu is in set to the G, and x is an integer. So if we forget the x, what we get is exactly a 2G rank lattice, but we add a G here. And now I can embed the Heisenberg group again in the symplectic group of dimension 2G as follows. So lambda and mu, I put the identity 0, 0 in these places of the matrix, and then I add lambda as a row vector here, mu as a row vector here, and then I add the transpose of mu as a column vector here, and the transpose of lambda as a column vector here, and this extra number x here. Now the key point is that I am claiming that this is an embedding, which in some sense I am telling you which is the low, the group law of this Heisenberg group. So the group law of this Heisenberg group is just the product in this higher Heisenberg group restricted to H. And then the Jacobi group is just the semi-direct product of these two subgroups in the symplectic group. So in the symplectic group, observe that I have the elements of this shape, which come from a symplectic group of rank 1 less, and I have the elements of this shape that come from the Heisenberg group, and then the product, the composite of these two subgroups will give me the Jacobi group. This is a semi-direct product where the symplectic group acts on the Heisenberg group, and just saying that this is a subgroup of the symplectic group, I am telling you what is the action of the symplectic group over the Heisenberg group. Okay, now what is the interest of this group? So one looks at the Siegel upper half plane, which are the set of matrices. Hg is the set of symmetric complex matrices of degree G, is G times G complex symmetric matrices, such that the imaginary part is definite positive. Then the group, the Jacobi group, acts on the product of the Siegel upper half plane, Hg, times C to the G, as follows. So if I have a matrix M that is A, B, C, D, and I have an element set on the Heisenberg group, and I take an element W in the complex plane. No, so set is an element on the Siegel upper half plane, sorry. So you have M a symplectic matrix, set an element on the Siegel half space, and W a row vector. Then the action of M and lambda mu x on this element set W acts as follows. Observe that here I am taking the usual action of the symplectic group and the Siegel upper half space, and then on the complex part, the Heisenberg group acts as translating by the lattice lambda set plus mu, and then one has to multiply also by this factor coming from the symplectic part. So this is the action of the Jacobi group on the product of the Siegel upper half plane and the C to the power G. Why we're interested in this action is because if I now look at the quotient, so Hg cross C to the Z divided by this group G, this is the universal stack of principally polarized abelian varieties. So this is a construction of the universal family of principal polarized abelian varieties. Of course, if one does not like work with stacks, one can always consider a neat subgroup of the Jacobi group. And we can, in fact, look at a neat subgroup gamma of the symplectic group and then enlarge it with the Heisenberg group and look at the quotient to get a quasi-projective variety. Okay. So now, what is a Siegel-Jacobi modular form of weight k and index m? So remember that the modular forms are indexed by an invariant, which is the weight. Now, Siegel-Jacobi forms are indexed by two invariants, which are the weight and the index. And then a Siegel-Jacobi modular forms of weight k and index m for a subgroup gamma of the symplectic group is just a holomorphic function f that goes from the Siegel upper half space times g to the g to the complex numbers, such that for every m in the subgroup gamma, I want that the value of the function f at the translate of set w by m has to be equal to the determinant of cz plus d to the power k. So this is the transformation under k. But then I also want this transformation, the exponential of 2 pi I m. And then here appears w times the value of the function on set w. And if I act by an element of the Heisenberg group, then I want that it satisfies this cocycle condition. So the function on the translate of the point by an element of the Heisenberg group is given by this exponential where the index appears. So observe that the index appears here, and the weight appears here. And also we need to add another condition, which is more or less the analogous to the condition in modular forms that they can extend at infinity. And this is written as follows. So any function that satisfies 1 and 2 will always have a Fourier expansion where f of set w can be written as a sum for all matrices T that are symmetric. So T is equal to T transpose and positive definite, and that are half integral. Half integral means that they are in the diagonal, they are integral, and outside the diagonal, they are at most 1/2 of an integer. Then the sum for all possible row vectors R of a coefficient C of T that depends on T and R, and then this exponential function of the depending on the trace of T times Z, and this exponential function that depends on the scalar product of W and R. For certain integer lambda G that depends on the group G and in some sense has to do with the width at the cusps. And the important thing is that the a coefficient CTR on this Fourier expansion is different from 0 only when the matrix 1 over lambda gamma T 1/2 of R 1/2 of Rm is a semi-definite positive matrix. Okay, so this is a condition at the cusps. And then we'll say that a Siegel-Jacobi modular form is called a cusp form if the condition 3, instead of saying that this matrix is semi-positive definite, is that the coefficient CTR is different from 0. This implies that this matrix is strictly positive definite. Now, in the world of Siegel-Jacobi forms, there exists also what is called a Kocher principle, which tells me that this last condition is not necessary. So if G is bigger or equal than 2, then any function that satisfies conditions 1 and 2 automatically satisfies condition 3. So there is no need to add this condition at the Fourier expansion when G is bigger or equal than 2, because it is automatic. Okay, and this is analogous to the Kocher principle for Siegel modular forms. That the interesting thing of the Kocher principle for Siegel modular forms is that it can be explained geometrically by the existence of the Satake compactification. So the Satake compactification is a compactification of the modular space of abelian varieties of genus G that has the property that the codimension of the boundary is bigger or equal than 2, which in fact implies that whenever I have a function which is defined outside the boundary, since the boundary has codimension at most 2, then it will be possible to extend it at the boundary. This is why in the case of Siegel modular forms, one has the Kocher principle. The Kocher principle for Siegel-Jacobi forms, in some sense, follows from the Kocher principle of Siegel modular forms. But in principle, there is no geometric explanation as before. Okay, now the line bundle of Siegel-Jacobi forms. So I again have my group gamma inside the symplectic group of matrices 2G by 2G integer matrices, and I assume that this group is neat, which means that it has no torsion, and that the quotient will be a nice variety. And then I will write AG of gamma. AG of gamma, this will be just the quotient of the Siegel upper half plane by this subgroup gamma of finite index. And then the UG gamma will be the quotient of AG cross CG divided by gamma semidirect product with the Heisenberg group. Then UG will be a family of principally polarized abelian varieties over AG gamma. And then the conditions 1 and 2 on the Siegel-Jacobi modular forms defines a cocycle for this group gamma cross AG set. And hence, they define a line bundle on L, also a line bundle that we will denote LKM, is the line bundle of weight K and index M of gamma on this UG of gamma. In such a way that now a Siegel modular form, a Siegel-Jacobi modular form can be seen as a section of the line bundle LKM on this open set UG gamma. Okay, so the Siegel-Jacobi forms of weight K and index M, JKM, are sections of this line bundle. And in fact, they are contained in the sections on the open set UG of this line bundle. And when G is bigger or equal than 0, then there is an equality. If G is, if G is bigger or equal than 2, sorry, this is an equality. If G is equal than 1, then we have a strict inclusion, and then we have to add this condition at the cusps. Okay, now questions we can ask on this group of modular forms. So one can easily see that if I look at the set, at the ring of all possible Siegel-Jacobi forms, the direct sum for all K and M bigger or equal than 0 of JKM of gamma, the set of all possible Siegel-Jacobi forms, this ring is not finitely generated. This can be seen as follows. So on the one hand, J0M, the Siegel-Jacobi forms of weight 0 and index M, this is always 0 for all M bigger than 0. On the other hand, the Jacobi forms of weight K and index M is always different from 0 for fixed K, as long as K is bigger than 0, and arbitrarily large M. So if I take arbitrarily large M, then I can get a Jacobi form of index of weight K and index M. And these two conditions automatically implies that this ring cannot be finitely generated, because if it is finitely generated, since J0M is 0, I will have a finite number of generators. They will have some weight and some K, so the ratio between the M and K will be, they will have a finite possible values. But for since JKM is different from 0 for fixed K and arbitrarily big M, we see that in this ring, the ratio between M and K is not bounded. So there cannot be a finite number of generators. So now the first question one can ask is, okay, so I know that the sum, the direct sum for all possible K's and M is not finitely generated, but what happens if I fix K and M and then I look only at the line generated by this fixed weight and fixed index? So I fix K and M, both strictly positive, and then I look at the direct sum for all L bigger or equal than 0 of the Siegel-Jacobi forms of weight L times K and index L times M. Is this ring finitely generated? And the next question, which is related and that then LKM extends to an ample line bundle, because this was the case for the usual modular forms. So one can ask if this is also true for Satake type, for this universal family of abelian varieties. And this condition is very tempting. So this second question is very tempting because it will explain geometrically the Köcher principle. And there is a paper by Runke, theta functions and Siegel-Jacobi forms in Acta Mathematica in '95, that states that the answer of both questions is positive. And the main aim of this talk is to say that no, that the answer to both questions is negative. So what we want to prove is that the algebra, the direct sum for all L bigger or equal than 0 of J, L, K, L, M is never finitely generated for any Km bigger than 0. And as a corollary, it cannot exist as a K-like compactification on UG such that the line bundle extends to something ample.
So the actual statements remain true, just your sort of the geometric interpretation is false. Is that the statement here?
Exactly. So the Köcher principle is true because what you do is to interpret the Siegel-Jacobi forms as Fourier coefficients of modular Jacobi forms, and then you use the Köcher principle for Siegel modular forms. Okay, so the Köcher principle is true because you use modular forms to prove it. What I claim is that it is not explained by the existence of a Satake type compactification. So this is
thanks.
Yeah. Okay, so then yeah, and in some sense we will see that the fact that it's never finitely generated, in some sense it has also to do with tropical geometry. In some sense it was the tropical picture which allows us to see that it cannot be finitely generated. Okay. Now the next interesting question is try to compute the dimension of the space of Siegel-Jacobi forms. Of course, possibly to be able to compute all these dimensions for all K and M is too difficult. So let's just compute the asymptotic growth of these dimensions. So we can try to compute the volume of this graded linear series. So we can try to compute the lim sub of the dimension of L, K, L, M of gamma divided by L to the D divided by D factorial, where now D is the dimension of this universal family of abelian varieties that will be G times G minus 1 over 2 plus G. Okay, this question was in some sense answered by Tai even before people were very interested in Siegel-Jacobi forms, and he obtains the following formula. So this asymptotic growth is given by this number, where it appears the dimension, it appears the index, it appears the weight, it appears also the index of the subgroup gamma we are using, the index inside the symplectic group, and it appears also the Bernoulli numbers, or if you prefer, the values of the zeta function. And this is in some sense related with the Siegel volume. Okay. Now the next question is whether there is an intersection theoretical interpretation of this dimension. So this dimension in the long run is a volume, and at least for ample divisors, for instance, we know that the volume is given by the degree. So then the next natural question is whether we can give an intersection theoretical interpretation to this asymptotic growth of Jacobi forms. The analogy will be that in the case of Siegel modular forms, we can look at the asymptotic growth. Again, there is an L missing here. I can look at the asymptotic growth of the dimension of M Lk of gamma divided by L to the power D prime factorial. And this is exactly the degree of the line bundle of modular forms. Okay. And now the answer, in some sense, as Anna hinted in her talk, is yes, we can give an intersection theoretical interpretation of this volume, but it is not the degree of a line bundle. It is the degree of a B divisor. Okay. So now, in order to get these results, we need now to introduce the canonical invariant metric on the line bundle of Siegel-Jacobi forms. Now the invariant metric on this line bundle is given explicitly as follows. So if I have a function f that satisfies the transformation rules of a Siegel-Jacobi forms, hence a section of the line bundle of Siegel-Jacobi forms, then I define the norm of the function as a section as the absolute value as a function. This is a function on the upper half plane times c to the z times the determinant of y to the k times this exponential of minus 4 pi m beta y minus 1 beta transpose. Here, the set is an element on the Siegel upper half space, which is written as x plus I y. Y will be the imaginary part, and W is an element of c to the z that is again written as alpha plus I beta with real part and imaginary part. Now, the point is that in principle, this is a function which is defined in the product of the upper half plane, sorry, the upper half space times c to the z, but using the fact that f is a Siegel-Jacobi form of weight k and index m, then one can see that this is really an invariant function that descends to the quotient. So this function is invariant under the axiom of gamma, and hence descends to a function on the universal family of abelian varieties and gives rise to a norm, to a metric on this line bundle. Now, when k and m are both positive, then this metric is PSH, at least PSH on the open part. So this is a metric, a smooth metric on the open part, and on the open part is PSH. Now, there is a proposition that tells me that if I look now at toroidal compactification of G gamma, that will depend on the choice of a fan in certain complex pi. So there is a combinatorial description of all toroidal compactifications. Then we can find a toroidal compactification in such a way that this line bundle, that in principle is a line bundle with a PSH metric on the open part, extends to a line bundle on the whole space with a toroidal PSH metric. And hence, we can use this metric and apply the theory that we have developed previously that relates PSH toroidal metrics with B divisors and with graded linear series. Okay, and then let's see how we can use this result to prove that the algebra, the direct sum for all L of LK LM of gamma is never finitely generated. First, there is a theorem by Ziegler that tells us that a holomorphic section F of gamma of the line bundle of Jacobi, Siegel-Jacobi forms on the open space UG of gamma, so it's a Siegel-Jacobi form, is a cusp Siegel-Jacobi form if and only if the norm of F is bounded. So this is the first condition, which in fact tells us that the ring, the graded linear series associated to this line bundle with this PSH metric is exactly the space of cusp Jacobi forms. So the space of cusp Jacobi forms can be recovered as the graded linear series associated with a line bundle with a PSH metric. And then there is another lemma that we can prove that tells me that if I look at the B divisor associated to the cusp Jacobi forms, or I look at the B divisor associated to all Jacobi forms, they are the same. So in some sense, the cusp Jacobi forms, the difference between being cusp or not being cusp is just whether they vanish at infinity or not. And then if we take higher and higher powers of LK, this will be negligible. And this implies that in the long run, they will give me exactly the same B divisor. And hence, the corollary of the results before is that the B divisor associated to the ring of Siegel-Jacobi forms is the same as the B divisor associated to the, the line bundle of Siegel-Jacobi forms with this metric, and we will call D to this B divisor. But now we can make an explicit computation, and by an explicit computation, because we have an explicit expression of the metric, we know if we know the metric, I have explained to you how we can look at the associated function on the on the conical complex associated to the B divisor, and we can show that this function is not piecewise linear. And remember that I told you before that if I have a graded linear series that is finitely generated, then the associated B divisor is Cartier, and if the associated B divisor is Cartier, then the associated function is not piecewise linear, since the associated the associated function has to be piecewise linear. Since the associated function is never piecewise linear, then we know that this graded linear series can never be finitely generated. So this is the first result, that this is never finitely generated. And then what about the asymptotic dimensions of the space of Siegel Jacobi forms? So now we know that this lim sup, using the Hilbert-Samuel theorem, turns out to be equal to the degree of the associated B divisor, and hence is equal to the integral on the open part of C1 of LK to dm. And then this integral is so now that we have written this as an integral, now it is an integral that is easy to compute explicitly once we know how to integrate on the Siegel upper half plane. And then integrating this form, we recover exactly this formula on this asymptotic dimension, but with the bonus that in some sense we give an intersection theoretical interpretation of this growth of functions. Okay, so thank you very much for your attention.